Welcome to the Deep Dive. We dive into complex research, stack up the source material, and figure out the nuggets of insight that matter most to you. Today we are focusing on a technical challenge that, well, it carries a colossal price tag. Back in 1982, material failure due to fracture cost the U.S. economy an estimated $119 billion a year.
Yeah, that number, while historical, it really sets the stakes, doesn't it? The sources make a pretty compelling argument. If we had adopted the best fracture control procedures available, then we could have potentially saved, what, $35 billion annually? So this is why reliable quantitative prediction isn't just academic. It's, absolutely vital for safety and economic health.
Right. So our mission today is to unpack a high-powered numerical strategy designed to deliver exactly those reliable predictions. We're looking at stress intensity factors, the SIFs, gobials. These are the critical metrics engineers rely on to predict and hopefully halt crack progression. And specifically, how one sophisticated numerical method ensures these metrics are both stable and highly accurate.
Exactly. We're specifically breaking down the performance of the p-Hierarchical discontinuous interpolant stable generalized finite element method, which is a mouthful, so thankfully it's shortened to pFEM-DSGFEM. And we're looking at it when it's paired with a clever, pretty low-cost technique for data extraction called the Displacement Correlation Method, or DCM.
Okay, so in short, we're asking, how do we take the sheer complexity of modern 3D fracture simulation and turn it into a stable, trustworthy, and importantly, fast predictive tool? A tool engineers can actually deploy when the cost of failure is measured in, well, billions.
Okay, let's maybe unpack the core challenge first. When you're modeling a complex 3D crack, standard finite element method pFEM, it forces you to mesh your geometry so the elements conform perfectly to the crack surface. And that's just computationally prohibitive and, frankly, massively complicated.
Which is why the Generalized Finite Element Method, GFM, sounds like salvation, right? It doesn't require the mesh to align with the crack. But why introduce this layer of mathematical complexity if it just creates new problems?
Well, because GFM fundamentally solves that huge problem of crack geometry complexity. It really does. It does this by using what we call enrichment functions. You can think of them as sort of preloaded data points, specifically discontinuous and singular branch functions. And they introduce a priori knowledge you already have about how the crack behaves right into the standard approximation space.
Ah, okay. So instead of making the computer brute force calculate those, insane mathematically singular stresses right at the crack tip, the singular enrichment functions essentially give the solution a sophisticated cheat sheet. They preload that known infinite stress pattern.
That's it, exactly. They approximate the singularity of the linear elastic solution right along the crack front. That's the real genius of GFM. But, like you said, that genius comes with a pretty devastating trade-off. Stability.
Yeah, that's the classic engineering headache, isn't it? Flexibility often leads to instability.
Totally. And in this context, the sources confirm that the condition number of the stiffness matrix, which is basically a measure of how sensitive your numerical result is to tiny input changes, it grows exponentially faster than in standard pFEM. So if you try to push the fidelity using high-order polynomial approximations, you very quickly hit ill-conditioning problems.
Okay, so for the engineer using this tool in, say, a design cycle, what does ill-conditioning actually look like? Does the simulation just politely crash? Or maybe worse, does it spit out a plausible but fundamentally wrong SIF number?
That's the real danger. It can lead to solutions that are just physically nonsensical. Or perhaps more insidiously, they might look reasonable but are fundamentally unreliable because the underlying matrix equations are just so highly sensitive. And that lack of stability, it erodes confidence, right? It defeats the entire purpose of doing the simulation in the first place.
Got it. So the pFEM-DSGFEM space is positioned as the stability answer here. How does this specific method manage to tame that instability that seems inherent in high-order GFM?
Right, so it tackles stability on basically two fronts. First, they make these subtle, what they call space-preserving modifications to the enrichment functions themselves. This just means simple things like shifting the function to 0 at the node and subtracting the piecewise linear interpolant. It's actually a common numerical trick to sort of reduce the range of values in the matrix, which helps stability.
Okay, that handles the math functions themselves, but what about the geometry issue, like where the crack physically cuts through an element?
Yeah, that's the second fix, and it's more structural. It's called node snapping. This is an algorithm specifically designed to prevent conditioning issues when those heaviside enrichment functions, the ones handling the jump across the crack cut, and nodes element support into two highly disparate proportions.
Hold on, disparate proportions. Can you put that in plain engineering terms? Are we talking about numerical instability because one tiny part of the element is essentially like massless compared to the other?
Precisely. Yeah, that's a good way to put it. If one side of an element that's cut by the crack is negligibly small, the resulting numerical system becomes highly unbalanced, unstable. So node snapping mitigates this. It algorithmically moves vertex nodes directly onto the crack's surface boundary if they get too close. It ensures the support isn't divided so unevenly that it causes instability. This robustness is absolutely critical.
And did their testing actually prove this stabilization worked in practice?
It did, yeah. They tested the challenging inclined edge crack problem, and the numerical confirmation was solid. The pFEM-DSGFEF space maintained growth in the scaled condition number, that key measure of matrix health, that was pretty much on pace with standard stable FEM. And crucially, they achieved this stability even when the domain was locally enriched up to a cubic approximation, which is quite demanding.
Okay, so if the original goal was, potentially saving the U.S. economy $35 billion by using reliable fracture control, this numerical stability, this condition number parity, that's the mechanism that delivers the confidence needed to actually trust the simulation, helping prevent over-engineering or, worse, component failure.
It's the foundation, absolutely. So now we have a robust, stable model of the stress field around the crack. But calculating that field is really only half the battle. We still need to extract those stress intensity factors, the SIFs, efficiently.
Right, and for those of us following the application of this method, the extraction phase is absolutely critical. The sources state the team opted for the Displacement Correlation Method, DCM. Why use DCM? Especially when energy-based methods like the interaction integral are often considered the sort of gold standard for accuracy.
That's a fair question. While those energy integral methods are highly accurate and have that nice path-independent property, they're also complex and computationally expensive. The literature confirms DCM is considerably less expensive, which makes it much more ideal for rapid industrial deployment. DCM works by calculating SIFs based on the relationship between the SIF themselves and the asymptotic displacement field near the crack tip. Specifically, it relies on measuring the jump in the displacement field right across the crack surface.
Okay, but the traditional downside of DCM is typically lower accuracy.
Right.
If the base calculation for DCM inherently has an order of error of what cal they are, how do they achieve the high precision needed for, say, life-critical fracture analysis?
Good point. They apply two crucial boosters, essentially, to clean up the signal and boost accuracy. The first is precision via something called Richardson extrapolation. They calculate the SIF approximation at two different points behind the crack front, call them Trinidad and dollars. Then they use extrapolation to mathematically push that result forward right to the crack front itself. And this mathematically increases the order of accuracy from that base mathcal up to a highly accurate mathcal row 2.
Okay, that's the precision piece. And the second booster for reliability, what's that?
Robustness via averaging. They don't just trust a single point calculation. That would be risky. Instead, they use an averaging scheme, pulling data from, I think it was $10 different sampling points around the crack front. This substantially reduces numerical noise, and it leads to SIF curves that are much smoother and much more reliable for any subsequent fracture propagation simulations you might want to do.
And this brings us to what seems like the crucial aha moment in the research, doesn't it? Because the underlying pFEM-DSGFEM solution is so highly accurate and stable, the DCM extraction process itself gains this surprising quality, path-independent-like robustness.
Yes. That's what's fascinating here. It's how the stability of the foundation really enhances the simplicity of the extraction method. This robustness means the accuracy of the extracted SIFs is not significantly influenced by the distance behind the crack front, that distance error, where the engineer actually decides to place their measurement tool, their virtual probe.
Wow, so less guesswork, less reliance on a potentially finicky post-processing step, and just more confidence in the final SIF curve. That sounds like it mimics the huge benefit of those really costly energy methods, but maybe at a fraction of the price. That's a massive practical benefit for the user, surely.
Absolutely. Less sensitivity to user input translates directly into more reliable simulations. It's a big deal.
I also noticed a quick note on adapting DCM for complex shapes. For non-planar, curved cracks, the basic DCM approach hits a bit of a snag because the extraction points might not actually be on the crack surface.
That's right, yeah. For a curved crack, the standard extraction points, which are typically taken perpendicular to the crack front and its local plane, they might sort of float off the actual curved surface. The fix is actually pretty straightforward, just a simple geometric correction. You orthogonally project those potential extraction points back onto the actual curved crack surface. This just ensures you're calculating the displacement jump across the correct boundary. Simple fix, but necessary.
Okay, great. So now that we understand the methodology stable model generation coupled with robust extraction, let's look at the proof. The sources validated this combined pFEM-DSGFEM-DCM approach across 4 pretty rigorous case studies. Let's start with case 1, the edge crack verification.
Right, this was the foundational test. It was a fully 3D problem designed specifically to ensure the boundary conditions were handled correctly by the method, and the SEF results align perfectly with known, highly accurate reference curves. Specifically, they matched boundary element method formulations, which are quite accurate, and also standard FEM solutions that use special techniques like quarter point nodes and the interaction integral implemented in commercial software like Abacus. So basically, it verified that the methodology works as advertised. Check.
Good start. Next, they moved on to the inclined elliptical crack. This is a standard mixed mode problem, but it has a curved crack front. What did the pFEM achieve here that the standard GFEM struggled with?
Well, it produced SIF curves that were just considerably smoother and more accurate than the standard GFEM spaces could manage. And the smoothness isn't just cosmetic, it's fundamentally important. Why? Because in fracture propagation simulations, jerky or noisy SIF curves lead to unstable or just plain unrealistic crack path predictions. Smoother SIFs mean more stable, believable simulations.
And this case also allowed them to compare different singular enrichment functions, OD6 versus OD9. For an audience that knows the topic, what's the crucial difference here in terms of the fracture modes being captured?
Okay, yeah, the difference really lies in the fidelity of the crack tip approximation. The OD6 function, it only represents mode 1, that's opening, and mode 2, in-plane sliding, and it treats them as uncoupled from mode 3, which is tearing or out-of-plane shear. The OD9 function, on the other hand, represents all 3 modes, 2 and 3 together, fully coupled. And since this inclined elliptical crack is a fully mixed mode problem, just ignoring or decoupling mode 3 is potentially dangerous.
And the numbers actually bore that out, didn't they?
Absolutely. By using the more comprehensive OD9 function, they saw a really substantial reduction in the mode 3 SIF error, almost 10% lower, I recall, compared to using the simpler OD6 function. It just reinforces the need to choose the correct high-fidelity enrichment functions that actually match the physics of the specific problem you're trying to solve.
Makes sense. Okay, let's move to case 3. The spherical cap crack. This was a non-planar curved crack, a major challenge. But the surprising finding here wasn't just about convergence. It was that the numerical method seemed to correct established analytical literature. That sounds bold.
It is. This is genuinely astonishing, actually. The simulations converged very consistently to a solution that was different from previously reported analytical values in the literature. And this immediately raises a big question, right? Why should you trust a numerical method over potentially decades of accepted, published analytical work?
Exactly. That sounds like professional heresy almost. What was the justification? How did they back up trusting their numerical convergence over the established results?
Well, they didn't just dismiss the prior work out of hand. They actually went back and meticulously followed the original analytical procedure step by step. And they found that the original solution for the infinite domain case had actually been miscalculated. A subtle error, but significant. They corrected the scaled SUF values for mode 1 to 0.889 and mode 2 to 0.245, I believe. And crucially, their numerical results converged perfectly to these corrected values. It was a powerful validation, proving the exceptional accuracy and rigor of the pFTS-GFM-MDCM approach.
Wow, okay. That level of detail and verification really does speak volumes about the method's reliability.
Wow.
What else did this non-planar case teach us about implementing the method effectively, especially for real-world complex geometry?
It really hammered home that even with the most stable numerical space, geometric fidelity still matters tremendously. You can't neglect the input. Specifically, the accuracy of the Mode 2 SIFs was quite sensitive to how well the crack surface itself was represented or meshed. And interestingly, it wasn't enough to just refine the crack surface circumferentially around the edge. Refinement in the direction of SIF extraction was specifically critical for getting Mode 2 right. It just confirms that the quality of your input geometry absolutely has to match the fidelity you're aiming for in the numerical solution. Garbage in, garbage out still applies.
Right. Good reminder. Finally, we get to case 4, the welded T-joint. This tested the practical applicability and, critically, the efficiency of the method on a complex, realistic structural engineering component. This is where we kind of bring that $119 billion problem full circle, thinking about potential cost savings in design.
Exactly. This was the efficiency litmus test. The main goal was to see if doing a local high-order analysis was actually viable in practice, because doing a full global cubic approximation, which you might consider the gold standard for fidelity, would have increased the total problem size by a staggering 225%. And for an iterative design process, an increase like that is basically a death sentence. It's just too slow, too expensive.
Which is why the final number they reported is so compelling. They only enriched the geometry locally, just around the crack front, up to that cubic approximation.
Precisely. And that local geometric enrichment increased the total problem size by only,
Okay.
wait for it, 6.6% compared to the baseline globally quadratic solution. Just think about the economic impact there. 6.6% versus 225%. It's a night and day.
That is massive. That low-cost jump in fidelity offers engineers an incredibly efficient way to just check if their standard globally quadratic soft solutions are actually converged and reliable. They can do this without the massive computational expense or, huge cloud computing costs required for a full global cubic analysis. It could dramatically speed up the design cycle.
Exactly. It ensures that the high-fidelity validation step is practically viable, not just theoretically possible. And that allows engineers to move faster and with much greater confidence in their results. This ties directly back to avoiding those huge costs of fracture we talked about right at the start.
So what does this all mean for you, the listener, if we synthesize the core success of this deep dive?
Well, I think the bottom line is that the combination of these numerically stable, high-order pFEM-DSGFEM spaces and that robust DCM extraction method, it really solves the three main hurdles in fracture simulation: accuracy, stability, and efficiency. It provides accurate, smooth, and critically, that path-independent like SIF extraction across a really wide spectrum of linear elastic fracture mechanics problems, even for complex non-planar geometries.
Yeah, and maybe the ultimate takeaway is that this stable foundation removes a lot of the guesswork. The numerical stability of the method gives engineers the confidence to rely on the robustness of the DCM extraction, which removes significant uncertainty and just makes the whole predictive process faster and cheaper.
Right. And this leads us to a final thought for you to maybe explore further. Given the demonstrated accuracy and stability of these methods for calculating static SIs, what complex future applications might now be within reach? Things like simulations of dynamic fracture propagation, where the crack is actually moving fast, or perhaps analyzing fracture in really complex anisotropic materials you find in advanced manufacturing. Are these now made computationally and practically possible?